Okay, in this segment, we're going to talk about human population genetics and how it impacts our understanding of pharmacogenomics. So I have to start out, and this is going to be treacherous, drawing a quick map of the world. So bear with me. So we're going to start out with North America. So we have Baja, and we have Central America, and then we have South America. Forgive me, this is highly stylized. Florida, Alaska is important. Okay, so there you go there. Then we have Africa, very important. Middle East, we have Europe. There's a couple little things like Spain and da-da-da. Okay, we have then India, we have Asia, Russia. There are a whole bunch of islands that they lead to Australia. And then remember, Alaska is over here too. Alaska. Okay, there's your map of the world. Didn't take too long. And this is kind of a big idea, but the general idea is that somewhere in Africa around here, about 150,000 years ago, is where the first Homo sapiens, indistinguishable from us, just like us. If you grabbed one of those babies, sent them to Stanford, they'd be rooting for the Stanford football team and taking classes, okay? Then there were population migrations. And this is the population we talked about, the very first population that had the very first human genomes that, of course, were having mutation and recombination, but they started out a small group. And then there were multiple, and this is a very brief summary of a very interesting and complicated field. But basically, these populations had several waves of migrations. In many ways, we're interested in the oldest migrations. So of course, they went throughout Africa. And one thing they did is they crossed into the Mideast, and they kind of wound up in Europe. They kind of wound up in northern China. They wound up in Australia. The ones that wound up in real north, in like Siberia, came across the Bering Strait, came down into the Americas, and then wound up eventually at the bottom of South America. Now, very complicated science has been done here, but if you want to put very rough numbers, and I'm mostly making up these numbers, all these numbers have a variance, and they change based on the discovery of new fossils and new skeletons. But just for the sake of argument, this was 150,000 years ago. This is about 90,000 years ago. This is about 60,000 years ago. That is the first arrival of humans to these areas. This is about 70,000 years ago. This is about 40,000 years ago to Australia. They didn't actually cross into Alaska until about 15,000 years ago. So this 15 is the same as this 15. And then they get to America. They get to here, Stanford. They get to Stanford and UCSF. UCSF is over there. They got to our region maybe 13,000 years ago. And then finally, they get to the tip of Patagonia about 11,000 years ago. So these are rough numbers. But they're interesting to think about because it gives you a framework for thinking about what we find in human populations when we look at the SNPs, for example. And we're focusing on SNPs because it's what we can measure the best. In all of these populations. So first of all, when we talk about ancestry, here, let me put this in a little purple box because it's not really part of the map. It's the topic. I'm going to actually probably put some of my notes like in the Pacific and Atlantic Ocean. I hope that's okay. A few things make a lot of sense in light of this map. So the first thing is the African population has been mutating and recombining for the longest amount of time, and so they have the most variation. Which means, because of the recombination, they have the most eroded LD. So sometimes we think about blocks of correlation. So you might imagine that there is a region where there hasn't been a lot of recombinations, so from one end to the other are still correlated. This would be called an LD block. It's a block where LD is still high. The LD blocks in African populations are smaller than the LD blocks, for example, in European populations because they've had more recombinations. And therefore, the distance you can go and still see the statistical signs of LD are the shortest. Okay, that's fine. We see a lot of variation. Interestingly, next important point is that most SNPs that are found in the world are found in Africa. So most SNPs are present in Africa, which means we had a lot of variation produced in Africa before people started leaving. And it is not the case that you go to different areas of the world and then have a lot of new SNPs created. That happens sometimes, but mostly not. Most populations share SNPs with the original African populations. However, there is what I would call a bottleneck effect, which is every time there was a migration, and I really shouldn't draw it as one migration. I'm going to draw this as a set of lines, because people left Africa to go into, for example, the Mideast, or even across like that, many times. Every time a population leaves Africa, there's something called the bottleneck effect. And what it has to do with is that, just think about it in real terms. This is usually a small band of men and women. If it was just men, then there wasn't a lot of reproduction going on, and we don't have any trace of that. So this had to be a set of men and women, probably in a small group, hundreds, maybe thousands, but not millions. There weren't millions of humans until relatively late. So they did not take all the SNPs out of Africa because they were just a subset of humans. And frankly, they were probably related. It might have been a clan or a family. So when a population leaves Africa, it takes a subset of SNPs. Which is why most SNPs that you see in humans are present in Africa. But there are some differences between the SNPs you see in Europe and the SNPs you see in Aboriginal Australians, the SNPs that you see in Native Americans, because the people who began those journeys didn't take all of the SNPs out of Africa. They took a subset of SNPs that their clan had, and so there's more variation, and I already told you this, has the most variation in Africa, and all the populations that left Africa have a subset of that variation. Based on the random chance of what they took or what their ancestors took when they left Africa. So, let me make sure I've made my points. Most SNPs are present. The bottleneck effect. They can get some new SNPs, but the new SNPs are relatively uncommon compared to the SNPs found in the African populations. And then when you draw a frequency of SNPs, you always get a picture like this. So for any population, you can plot the mean allele frequency, minor allele frequency, which goes from 0 to 0.5. Remember, if it's more than 0.5, it would be the major allele. Minor allele frequency versus the frequency of that minor allele frequency in the population of interest. And it typically looks like this. And it might be steeper, it might be less steep. This would be for population 1, population 2, population 3. Let's just think about it. Which population would have, so first of all, lots of good things here. So this is frequency. And what it's telling you is these are very rare SNPs, like 0.0001%. These are very common SNPs because it's up to 0.5. if you see, and so you can study this for hours, and I'm not going to discuss it for hours, but you can imagine that if you have an old population, that you have a lot of variation, then you're going to have a little bit of a shift to the right because you just, well, population 3 looks like an older population here. It has more total SNPs because the area under this curve is the highest, which means it has the most SNPs, and it has the biggest spread of SNPs between 0 and 0.5. Population 1 is kind of the newest population because it has the least total number of SNPs that it shares, that's related to the area under the curve, and they're shifted towards mean allele frequencies that are lower. That doesn't follow necessarily, but the area under the curve argument does. So why am I saying this? It raises the issue that SNPs can be common or rare. That affects some of the experiments that we do for discovery of pharmacogenomic variation in a way that I will talk about later. But I do want to just point out that for any population, you can have what they call the frequency spectrum of the SNPs in that population. And by studying that spectrum, you can learn things about the age of the population and the diversity of the population.